probably like to see what's going on as well. All right, let me wait for that to turn on. Well, yeah, while the projector's turning on. So the homework, I went ahead and graded it. So for those of you who have shown up, did you turn in a homework physically or online?
It was online.
It was on. Okay, so you already got your feedback. So yeah, so for those of you who turned it in online, you could see your feedback from the file you shared with me. You should be able to go access that, and I left comments for whether you got the problem right or wrong, and then what issues I had with it. If you have any questions on either the comments I made or about any question, because I didn't grade every question, I graded intermittent questions. If you have any questions about those, if you did it right or wrong, you could just shoot me an email and ask. Just say, hey, did I do this one right? Did I do it wrong? Or, they're not really tough to grade. At least not for now anyways, or in the very beginning. And from last class, I did assign sections 1.3 and 1.4. Those are both due Tuesday. I'll send out an email after class with that, and then another homework assignment I'll have later on. But just to give everyone a heads up. So I'll send out an email to clarify that. And so I think that is all I can think of. So let's go ahead and get started. And so we last time we finished up everything in section 1.4 using definitions of trig functions. And so now we're going to pick up on the new chapter. Chapter 2 being, well, just a discussion on acute angles and right triangles. And so this is pretty much going to be a natural extension of the trig functions, how we can use them to get some interesting information as well as some other properties. I feel as though, yes, so I am making a slight change to this homework. Just getting rid of 13. Was it 13? Let me make sure. Pretty sure it was 13. Yeah, so I'm taking off 13. Just one less problem. Oh, all right. I do not have the right thing. 1 second. There we go. All right, let's try that again. Acute angles and right triangles. So just 13 is gone. Ignore 13. I'll emphasize that in the email as well. So here we're just going to look at properties of acute angles and right triangles. So it's mainly going to be a continuation of what we talked about last time. And so example 1 starts off, I think, fairly tame. Find sine, cosine, and tangent for angles A and B. And since we have a right triangle, we can utilize the opposite, adjacent, and hypotenuse thing. We'll start off with angle A, which is, of course, this angle. So if we're looking for sine of A, well, the good thing here is that since the triangle already has the segments filled out, we just have to apply, well, so let's see, sine is opposite over hypotenuse. So opposite of A is 7, and the hypotenuse seems to be 25. Cosine of A, that one was adjacent over hypotenuse. Adjacent is 24, and then the hypotenuse again is 25. And of course, tangent of A was opposite over adjacent. And that would be 7 over 24. So some stuff we've already talked about before. It's just a nice refresher. But that is the good thing about having a right triangle. If we have a right triangle, then we can utilize opposite, adjacent, and hypotenuse. It wants to know the same thing for angle B. Angle B being this angle up here. I'll do it in a different color. And same idea. It wants us to figure out sine, cosine, and tangent of, well, B. So sine of B, well, it's still opposite over hypotenuse. The only difference here, the opposite here is not the same opposite as for angle A. So that's when changing an angle may change what opposite is and what adjacent is. Hypotenuse stays the same because the hypotenuse is always the slanted line, always the diagonal line in the triangle. So here the opposite of B is 24. And then the hypotenuse is 25. So this is different than for angle A, where the opposite value was 7. But if you understand that, then the rest of these shouldn't be too bad. Cosine of B is adjacent over hypotenuse. And now adjacent is 7. So not 24 like it was for angle A. And tangent of B, opposite over adjacent, which is 24 over 7. So what this illustrates is your choice of angle will change the output of sine, cosine, and tangent, because it's all relative to what is across from the angle and what is adjacent to the segment adjacent to that aforementioned side. Does anyone have any questions about this so far? Google Meet people? Okay. I did start recording. Yes, I did. Okay, cool. So let's scroll down a little bit. And we're going to talk a little bit about cofunctions. So these idea of cofunctions. So we've related trigonometric functions by reciprocals. So sine and cosecant are reciprocals. Cosine and secant are reciprocals. Cotangent and tangent are reciprocals. But we can also associate certain pairs of functions by this idea of cofunctions, as in one is simply a shift of 90 degrees from the other. And so this is a way to associate sine and cosine, as you can see for this first one. Sine and cosine, and equivalently right below it, cosine and sine. It's a way of rewriting one trig function to another, if you needed to do so, as we'll see ahead in the next 2 examples, I think. It also associates secant and cosecant. And tangent and cotangent, it's another way of associating them, because they're already reciprocal. They're already reciprocally associated. Now they're also associated as cofunctions. And this is actually where the namesake comes from. Sine and cosine, secant and cosecant, tangent and cotangent. That's where the name comes from. So that one's much easier to determine. If, say, that came up on a test or something, what is the cofunction? Well, the prefix of co should really give that away, I would hope. And so with these formulas in mind, let's go ahead and scroll down a little bit to just example 2 here, which says write each function in terms of its cofunction. So for example 1 here, or part 1 in example 2, we want to write sine of 22 degrees in terms of its cofunction. Well, what's the co-function of sine? Actually, it's cosine. See, just an addition of a prefix. And so we are rewriting this as its co-function, so we're going to use cosine. And so what does the formula tell us to do to go from sine to cosine? It says, write down 90 degrees no matter what, and then subtract from that whatever angle was there before. That's what the formula says. I'm just following exactly what that formula says that I put a little asterisk next to. Hopefully we can all do 90 minus 22. And that's it. So that would be a function rewritten in terms of its cofunction. We have written sine in terms of cosine now. All right. What about cosecant? What is the cofunction of cosecant? Secant. Yeah, because of course it's not cosecant, because that doesn't make sense. The prefix is already there, so you can simply remove the prefix. So cosecant, its cofunction is just secant. And you can see that up here. So that brings us to secant. And notice all of these formulas are the exact same in regards to the input. It says just write down 90 degrees no matter what, and then subtract by whatever was there originally. And that would be it. So that's all you have to do. Nothing too crazy. Does anyone have any questions up to this point? Feels though so far this should be fairly straightforward.
It's not really a question about how you got it. It's so if you did that just like that on the homework, would that count as showing your work, or do you have to actually show up the scratch work? If you just did it in your head, 90 minus 81 is 9, would that be good enough for showing your work?
I mean, what I have here would be perfectly sufficient. Just, by jotting down. So yeah, that's the thing with your homework. Some of you did not show your work in certain places. And well, naturally that's not good. I need to see your process. I mean, I think the odd numbered problems are given in the back of the book. So when you just place the answer, my assumption is, well, you could have got it just straight from there. So, if you were to do this problem and then you just skip down from here to here, I'm naturally going to ask, where did that 9 come from? In your mind, you might know where the 9 comes from, but from my perspective,
you can't see that we knew how to get it.
Yeah, and as an instructor, I have to make an assumption, probably a callous assumption about where this answer could have come from. So naturally, intermediate steps are always helpful. Definitely helpful, in fact, required. And as far as how many steps go, I think it's going to be that the answer is going to be as clear as my notes. The amount of work I show in my notes should be equivalent to the amount of work you show for an equivalent problem in the homework. That's really all I can say on that. There's no definitive answer for that. But yeah, this would be fine. So we're going to look at the same thing. So I'm going to keep those formulas at the top. And we're also going to look at example 3, which is actually kind of similar to a problem we looked at I think it was the previous section, where we have to find one solution for this equation. So we had one problem, I believe it was in the last section, where we had to use a reciprocal identity to get the same trig function on both sides. Obviously here, we cannot use a reciprocal identity to get the same trig function on both sides, because sine and cosine are not related that way. If only we knew a way in which sine and cosine were related. Wait a minute, they're cofunctions. So in order to work out these, really they're trig equations, we have to either rewrite sine as cosine or cosine as sine. And really it doesn't matter which one is which, we just need the same trig function on both sides. In my notes, I switched cosine to sine. So this would be, okay, so this would be work off to the side, in other words. So I'm going to take cosine of 3 alpha minus 10 degrees. So this is kind of work off to the side. I'm going to rewrite this one. So we're ignoring that sine of 2 whatever plus 15 for now. We're going to take this and, well, rewrite it in terms of its cofunction. My motivation for thinking cofunction is this is how we get sine or cosine in terms of sine. So the question now is, how do we do that? And so we use the formula up here, which tells us how to do so. It says we can write sine. It says throw in 90 degrees no matter what, and then subtract what was originally there. Now, you subtract that whole angle. I'm keeping that whole angle in parentheses. So notice it's minus 3 alpha minus 10. I put parentheses because that minus sign needs to distribute. So I'm subtracting that whole angle, not just one part of the angle, the whole angle. So by simply distributing that negative sign, we get 90 degrees minus 3 alpha plus 10 degrees. I also see like terms, the 90 degrees and the 10 degrees. They're like terms. I can go ahead and throw those together right fast. And we have now rewritten cosine of 3 alpha as sine of 100 degrees. We've now rewritten cosine of 3 alpha minus 10 as sine of 100 degrees minus 3 alpha. And now we're going to go back to the statement of the problem and now use the sine of 100 degrees minus 3 alpha, because now we have the same trig function on both sides, which is great. So now we're returning. Almost had enough room. Let me try that again. So now this is what we're returning to. Now that we've swapped out the cosine part for its equivalent sine part, and conveniently here, we can, since we're looking for one solution, we can just cancel out these signs. That was the whole point. That's why we went through all of this hassle, just to do that. So now we have 2 alpha plus 15 degrees is equal to 100 degrees minus 3 alpha. And since algebra is a prerequisite for this class, I'm just going to breeze through the like terms and solve for alpha is 17 degrees. I hope it's 17.
Yeah.
All right, cool. So that would be the answer. Alpha is equal to 17 degrees. So that's one application of cofunctions. We can use it to manipulate an equation and find a solution algebraically by getting the same trig function on both sides. Does anyone have any questions about this? Okay. Now we're going to get to the important stuff. So cofunctions, yeah, that's cool. Special triangles. This is super important. I can't grasp how much of a necessity this is to the remainder of the semester. I preface this by saying certain angles such as 30 degrees, 45 degrees, 60 degrees, they occur pretty often. So those angles, we're going to call them special angles. And the triangles that they comprise are going to be called special triangles. It's triangles that have either 60 degrees, 30 degrees, or 45 degrees. So what I did was I provided the special triangles for you with one catch that I need to fill in. Let me try that again. So in the red, that's 30 degrees, and in black, this will be 60 degrees. So go ahead and make that addition to your notes, because that does matter, and it will matter for reasons we will get to. So on the, and remember that square, the box in the corner, that just means a right triangle. So that means the sum of the other two angles has to equal 90. And this is verified by the fact that 30 plus 60 is in fact 90. Now 45 degree right triangle, it's not as much to emphasize it here because we know that both of them are 45. And this is very helpful because we get, for these angles, we get, well, these are segments that need to be memorized, or at least quickly accessible. And as such, since these triangles are special, then that means these trig values below are going to be special. And they're going to come up quite a lot, the values that we're about to find out for parts 1 and 2 here. So for example 4, and I'll have the special triangles up here. So what we're going to start off doing is figuring out sine, cosine, and tangent for 45 degrees. And so the way we would do this before, if we're given an angle, we would draw out an XY plane. And we would plot out 45 degrees. So that would actually perfectly bisect the first quadrant. So that would be 45. And we would triangulate. But since we have the special triangle to our advantage, So the one up here in the top right, then we know how to fill out this triangle. So I'm going to bring the triangle off to the side here. So what's interesting is that the triangle I just illustrated is not, it's not really in the same orientation as the triangle up here. It doesn't have to be. There are going to be some nuances to this, and I'll explain those when that time comes. But in the meantime, across from 45, if we follow this diagram, well, since they're both 45, it doesn't matter. It tells us that one would be across from 45, another one would be across from the other 45, and then we put the square root of 2 as the hypotenuse. It tells us exactly how to fill in the triangle. And once we have the triangle figured out, well, we can figure out the trig functions by using opposite, adjacent, and hypotenuse. So now, sine of 45 degrees, well, what's opposite? That's 1. What's the hypotenuse? It's the square root of 2. In fact, I'm going to make some room here. I filled in the segments over on the far left. So I'll put in sine of 45 degrees. Yeah, so opposite is 1. The hypotenuse is square root of 2. And something you will notice in this homework set, if you do some of these problems and look in the back of the book, they may rationalize the denominator. Again, I don't ask you to rationalize the denominator. The book does it because the book wants to seem really smart. And I bet it is. So if you look in the back of the book and you think to yourself, I must have gotten the wrong answer because my answer doesn't look like their answer, that may not be the case. So I am going to put the rationalized form. Just, you don't have to rationalize it. But if you see answers like this in the back of the book, then I'm just showing you, and this is what they might look like. And if you really want to learn how to rationalize a denominator, I'd recommend you just look it up. There's probably some really easy tutorial on it. And I can show you, that's fine, but. We'll move on to cosine of 45 degrees. So cosine is adjacent over hypotenuse. Adjacent of 45, it also seems to be 1 over the square root of 2. So we get the same exact answer, which is okay in this case. That's fine. And then tangent. So it is opposite over adjacent, and they're both 1. So tangent of 45 degrees is just 1. Does anyone have any questions about this so far? Problem 2 is going to hopefully fill in any gaps you may have. Does anyone have any preliminary questions so far? Okay. All right, we're going to do the same exact thing, but for 60 degrees. So if we were to start off with an XY plane and plot 60 degrees, that's going to be a little bit steeper. So 60 degrees, and we triangulate. So now we do not have a 45-45 special triangle. we have a 30-60 special triangle. And now the question lies in, well, 30-60, that's two different numbers, unlike the 45-45. So this one's a little bit more important because this one, you have to choose the right number that goes across from 60. Because if you notice the 30-60 right triangle up here, across from 60 is the square root of 3. So you have to put the square root of 3 across from 60. So you can't just mix and match. You have to, we didn't have to worry about this before because, yeah, before both of them were 45. So they both had an opposite magnitude of 1. So that one is the square root of 3, which means the other one would have to be 1. So the adjacent, and then the hypotenuse would have to be 2. And notice that the triangle above up here is not oriented in the same way as the triangle we just illustrated. You have to use that information to your advantage. So you have to know which one is across and have to construct it by knowing the components of the triangle. And from here, contingent upon the correct construction of the triangle, they want us to find cosine of 60 degrees, or they call it beta. Fine. Cosine of 60 degrees. So cosine is adjacent over hypotenuse. Seems to be 1 over 2. Tangent of 60 degrees. Tangent is opposite over adjacent. Seems to simplify fairly quickly. And they also ask for cosecant. And cosecant, well, cosecant is just sine flipped. Yeah, it's going to be hypotenuse over opposite. The hypotenuse is 2, and the opposite, where are we at? Square root of 3. So again, I would accept this answer, but if you have to, or if you want to rationalize the denominator, I know some students over the summer, they prefer to rationalize it for whatever reason. If you want to, fine, that would be it, but you don't have to. If the directions say do it, I'm telling you, you don't have to. You can if you want. But that is really the idea for special triangles. This is how we apply them. And this is how we use special triangles to figure out trig values of special angles. And we'll see how this is more prevalent actually in example 5. Does anyone have any questions up to here? Okay. So now we go down to example 5, and then it says, figure out all the missing sides, pretty much. Here's kind of these two triangles shoved together. Try to find all the sides. So really, we have two triangles. And the goal, in fact, we've had problems with two triangles before. I think it was the two triangles that kind of faced towards each other. And I think you had one on your homework as well, maybe 1 or 2. So what we did was broke apart the two triangles and look at them separately. Now, one of these triangles is a lot more helpful to work with than the other. There's a certain reason why. So I'm just taking the leftmost triangle and rewriting it just off to the side. And I'll do the same for the left one. One of these triangles is much more helpful than the other. The reason why it's the left one is because it actually has a number. The right one doesn't have any numbers. Let me draw that a little bit larger. So we're going to pick the left one, and we'll see why that 9 being available makes things so much more helpful. Now, that leftmost triangle, so it is a special triangle, but since they gave us the 9 for the hypotenuse, that means that we do not use the sides from the 30-60 special triangle from above. And you might think, well, what was the point of even going over that? Well, the point is that, and I'm going to draw that triangle again. So the triangle that was above, what the diagram had, if 30 is down here, then we see the thing that's across from 30 is 1. So 1 would be here, square root of 3 would be down here, and 2 would be here. And what we did was, they're not the same triangle or congruent in that sense, but they're similar triangles. We've already talked about similar triangles. Similar triangles, the ratios of the corresponding sides are the same. So we can manipulate that to figure out x and y. So it doesn't mean that every triangle that has 30 degrees as one of its angles, it doesn't mean that its sides have to be 1, square root of 3, and 2. What it generalizes to is that every angle with 30 or 60 degrees is similar to this triangle. And that's the important part here. So now we can use, so these are similar triangles. And that's important because, like I said, the ratios of the corresponding sides are equal, which means that 9, the ratio between 9 and 2 is going to be the same as the ratio of any other two sides. So let's do the easy one first. Y and 1. So that ratio. And the reason why that's the easier one is y divided by 1 is just y. We don't even have to cross multiply. That's it. Okay, so what about x? So now we have that 9 over 2. That ratio is equal to x over the square root of 3. And what you get is that x is 9. When you multiply the square root of 3 on both sides, you get 9 square root of 3 over 2. And that is x. It's not a very pretty answer by any means, but again, it's just kind of moving numbers around in a particular manner. But that would be x and y. You could have also found x by using the Pythagorean theorem. You can always use that if you have a right triangle and know two of the three sides. It's just that the numbers would get kind of messy. In fact, they'd get really messy. And there's a time and a place for it, which I will talk about in the coming weeks. So that just takes care of x and y. And so that's the reason why the 9 in the very beginning was so important. It's because we needed one of those ratios to not have variables in it, so we can make this an algebra problem. So the reason why that's helpful is because we can go over to this rightmost triangle and give it some life. Because that was a segment that was shared between the two triangles, and we figured out that y was 9/2. So now we can do the same thing for this triangle, which it is a 30-60 triangle, which means it will be similar. It will be similar to a 30-60 triangle, where all the segments are known. Square root of 3 has to be across from 60, which means 1 would have to be across from 30, and then the hypotenuse is 2. And I got all of that from the special 30-60 triangle. So from here, it's the same idea. We use ratios to our advantage. So here we see that 9/2 and square root of 3, that ratio, so 9/2 over square root of 3 is going to be equal to, let's pick the easy one, z/1. I don't really like complex fractions, so if you cross multiply here, it'll kind of work itself out a little bit. 9/2 is equal to square root of 3 times z. And then by dividing the square root of 3 on both sides, you would get that z is equal to 9 divided by 2 square root of 3. We're not done because we have one more. Hopefully I can incorporate that here. We still have to find w. So w and 2. So 9/2 relates to square root of 3. That ratio is going to be equal to w relating to 2. Luckily, 9/2 times 2, the 2's cancel out, which is why there's only a 9 there. I really have no more space on here, really. So 9/2, yeah, so this one, 9/2 times 2, the 2's cancel and you just get 9. Then square root of 3w for the other one. That's 9 over square root of 3. I'm curious about something. Let's check one thing. So for 76 in the homework, 76 is just like this one. The answers are not going to be that nice. In fact, actually, I think for this one, for last semester, I gave a hint for number 76. So I'm going to scroll back down in a second. For 76, I gave one of the angle value, or I gave you one of the side values, since this is an even numbered problem. So for 76, the hint, what hint did I give? Which one of these would be good to give away? So to know, I'm not giving you the answer, but this would be if you're on the right track. I think it was A that I gave. That's the rationalized form, which means the answer you might get if you do it and don't rationalize the denominator. How did that work? 3 square root of 3. How does that work? Actually, I'll do this. Got one even better. So whatever answer you get, if you plug that in the calculator and get something like this, you're on the right track. And you can keep your form. Your form will actually probably, well, your form's fine. The book, like I said, the book likes to rationalize, and this is the rationalized form. I don't feel like figuring out the not rationalized form. So the decimal should be perfectly sufficient. That's for A. So that's not the whole problem. When you get to the problem, hopefully this will make sense. But that's your hint for number 76, is that if you get that, whatever answer you get for A, if you punch that in the calculator and you get that approximation, you're on the right track. Because that one I think is a little challenging, a little messy. So go ahead and make sure you have that, or you know how to reference it when I post the video. But other than that, example 5 looks like a complete war zone. But, and if any of you are Falcons fans, you might also enjoy the color scheme. But besides for that, any questions about anything? Are the Saints going to win the NFC South this year?
It's going to be a tougher race with the Buccaneers. I like
Still
it.
got it.
I like it, yeah.
It's going to be an interesting season if it happens.
Healthy Kamara then, for sure.
No. No. Well, it's not going to be the Panthers. I think we can all agree on that one.
Hey, the Panthers' offense is going to be good, man. Joe Brady's going to be really good.
I definitely, you know, that was the offensive coordinator at LSU, right?
Yeah, the coach.
Well, I don't know. Putting a new team together, it always
Yeah,
has
gonna
its
be slow.
bumps.
I think in 2 to 3 years, I think they'll be good.
I'm just always afraid of the Falcons. I'm just always afraid that one year they're just gonna.
It's because they play really hard against the Saints, no matter how bad they are.
And Matt Ryan is he puts up MVP numbers all the time.
All the time.
His defense just. Anyways, okay. So football aside, so yeah, that homework. So I didn't mention I was going to assign this homework not for Tuesday because that'd be way too many sections at once. Do Tuesday. What I was going to do for 2.1 and eventually 2.2. So the first assessment, not test. You don't have to take it in here. You take it on your own through Moodle. That assessment is going to be. When did I say you could take that? the 14th and the 15th, I think my email said. And as such, I need to get your homework in at an adequate time so I can grade it and give you feedback. This section and the next section are incredibly important. So what I was thinking was 2.1 and 2.2. The way I'm going to do it is if you want to turn it in person, and I'll say this in the email. If you want to turn those in person, you have to turn it in Thursday, or you got to slip it under my office door on Friday at some time. If you turn it in online, you can turn it in Friday at any time, 11:59 p.m. Or physically, you can put it under my office door. I'll see it, and you'll be good to go. So pretty much the deadline is Friday at 11:59 p.m. However you get it to me, find a way. The safe bet would be you could bring it in Thursday if you want. But that's my stipulation here. And I'll mention that in the email because you got over a week. So hopefully that's fair. And then by then I can grade it really quickly and give you all feedback so you don't make the same mistakes on the test.
So that's going to be 2.1 and 2.2.
Yes. 2.3 and 2.4 I'm still thinking about, but 2.1 and 2.2 are very important. I got to make sure you know how to do those two. Okay, so with all of that being said, Matt is trying. Well, his numbers pretty good.
That's because they're always behind and he's political.
It's because his defense always allows touchdowns too quickly, so he has more chances to pad his stats. Okay, so we move on. So in the last section, we were looking at acute angles. Remember, acute angles were the really narrow angles, which is why it was so natural to talk about 30 degrees, 45 degrees, and 60-degree angles. So what about non-acute angles? So pretty much obtuse angles, and then angles even larger than that don't even have a definitive name. So reference angles, this is going to be the most important thing I talk about in this whole unit, reference angles. So a reference angle is a way to take a larger angle and reduce it down to an acute angle. Now, it doesn't mean that you take the larger angle, you reduce it to an acute angle, and they're the same angle. But when you look at it from a trig function perspective, the trig function doesn't care. And I'm going to explain what all that means, but that's pretty much the general idea. So a reference angle, just some characteristics about it. It's got this denotation as theta with a little apostrophe next to it. So if you see me use that, that's what it means. It's always positive and it's always acute, which means it has to be between 0 and 90 degrees. And we've actually illustrated reference angles before, and I've just never referred to them as reference angles. You'll see, but it's whenever we triangulate, it's the angle of that triangle. That's what a reference angle is. It's the angle of the triangle whenever we triangulate. And again, this whole section is going to be filled with problems of this caliber. So it's the positive acute angle made by the terminal side with the x-axis. So in other words, the angle of the triangulation. So I want to.
If it's always positive or acute, does that mean it's always in quadrant 1?
Well,
Unless it's like the x is negative.
Well, it's not like. Well, if we were to draw the reference angle off to the side, then that would be in quadrant 1. Let me show the first two examples here, and then you can ask me that question in that case. So here I'll give an example of an angle in quadrant 2. So remember, we always start over here, and then some angle in quadrant 2. I'll just draw some random one. So this is just to visualize it. So here there's no value for, I'm not giving a value for theta quite yet. So that would be theta. The reference angle, so we're used to triangulating, which I'm going to do here. And so the reference angle, like I've mentioned, is the angle of that triangle we created. That's it. That's the reference angle. And then for an angle in quadrant 3, so I'll draw any angle in quadrant 3, it doesn't matter. So this would be theta. When we triangulate, the reference angle would be here. It's the angle of the triangle. It's the angle of it's the interior angle of the triangle we create when we triangulate. So naturally, what this illustration sort of supports is that there's not really a straightforward formula for determining it. You really need to know which quadrant your angle is in order for you to figure out your reference angle. And we'll see that in example 2. So this was just a visual representation, and we're going to be using visual representations for these questions. So let's go right here. So we're going to find the reference angle for each of these just random angles. So we'll also go ahead and plot these on an XY plane. So number 1 here, 140 degrees. So let's go ahead and put that on an XY plane. So 140 degrees, we think about what quadrant is that in. So we always start at the positive x-axis. Going here would be 90 degrees. If we go to the next axis, that would be 180, so that's too much. We only want to go to 140, so about there. So we see that this angle of 140 degrees lies in quadrant 2. And it's determining the quadrant mainly goes by how many degrees of 90 can you take out. So quadrant 2. And from here, we need to figure out the reference angle, which remember, that is when we triangulate. I'll try to put that here. What is, I can't get other colors, cool. What is, this angle? It's in blue. So let's think about that kind of intuitively. If we know that that initial red arc is 140 degrees, and we know that going to the full flat line would be 180 degrees, sort of arithmetic would make sense to find that blue arc.
180 to 140.
Yeah, it'd be 180 minus 140. So 180 would be all the way to the other part of the x-axis, and then we're subtracting off 140 to get the reference angle, which is just 40 degrees. And so that would be your reference angle, which we call, if you hear me say theta prime, it's the same thing as this. So that would be our answer for the reference angle. Well, let's look at problem 2. What I generally like to do is with negative angles, I like to view negative angles in terms of, so this might sound familiar. I like to view negative angles in terms of its least positive coterminal angle. So hopefully you all remember how to do that. The coterminal stuff, it's multiples of 360. Well, we want the least positive, so it would make sense to add 360. So the first thing I want to do is just negative 175 plus 360. This is so we can get a much easier angle to deal with. So this is one reason why coterminal angles are very, very nice to work with. Negative 175 plus 360 is positive 185. I'm going to rewrite that. 1 second. Negative 175 plus 360 is 185. So really what this tells us, they're not equal. These are not equal. I'm going to do this because they're congruent. They're not equal. They're not the same angle. But that's kind of the math person in me. You can think of them as equal, really, but to me, I know they're not equal. They're just equivalent or congruent in a sense. If you illustrate both of them on the XY plane, they will end up in the exact same spot. That's what it means to be coterminal. And that's why you can kind of think of them as the same thing. So really, we'll do this whole problem and just pretend like negative 175 doesn't exist. I might need a little bit more room here. This over here. Okay, so now the next goal is to figure out where negative 185 lies. And so if we start here, going to the first axis is 90 degrees. So far, so good. Going to the next one is 180. We have 185, so we have enough to spare. And then for that final 5 degrees, because we went 180 of the 185, it's just going to jet out a little bit further. In other words, this is something in quadrant 3. And if we triangulate, what it wants to know is what's this angle? The angle that I just highlighted in blue. It wants to know that angle. So now, intuitively, how would we figure out that angle using this visual representation? It's 185 minus 180. 185 is the full red part. And then 180 is where the flat line, the horizontal line is at. So as you can see, there's not a specific formula for this. It's a matter of, so 185 is the whole red arc. 180 is the horizontal. And the leftover part is 5 degrees. So again, in one case, we had to subtract the given angle by 180. And then before, we took 180 minus the original angle. So depending on which quadrant you're in, you will have to do something different. That's what I'm trying to emphasize. It doesn't really conform to a formula. It's kind of situational. And these are the situations contingent upon the quadrant. So yeah, that would just be, so that would be it. That's it. Okay, cool. so then we have some more to look at. So for problem 3, now we're going to find the reference angle of 422. So I'm not going to use 422 degrees. It's a little bit too large. We want to find its least positive coterminal angle. We can get this number even smaller. How do we do that? We can subtract 360. So numbers larger than 360, we can reduce by using its coterminal counterpart. So that's how I was able to look at this so quickly and determine, hey, I can get this smaller. It's because this number is bigger than 360. So really what I want to do, so this is going to be congruent to 422 minus 360. And where does the 62 come from?
Sure.
It's just 422 minus 360. So now for the rest of the problem, we could just look at 62. And we can ignore 422. So now we ask ourselves, where does that angle lie? So where does 62 degrees lie? Well, look at that. It ends up in quadrant 1. So it seems almost too trivial in a sense. So we found that 62 degrees is in quadrant 1, and we illustrated it and we triangulated the same way. So I guess the question is, what is the reference angle going to be? Well, same thing. So guess what? We don't have to do anything. This is one of those cases where the angle is the reference angle. That's the situation for quadrant 1. It's because we already have an angle that is positive, acute. Yeah, it's a positive acute angle. Before, we didn't have that. And we had to subtract 180 or subtract it from 180. Here, we already have a positive acute angle. So we don't have to do anything. The reference angle is 62 degrees. We don't have to do anything. So as you can tell, that's the easy one.
What if you get an angle that's like a sum of 90 degrees? Like that would be like 90, 180, 270.
So that's a good question. Quadrantals do not have reference angles. We end up just solving them by using you draw the point, and that's how it always is. So yeah, so that's a good thing to address. Quadrantals do not have reference angles because there's no way to triangulate, which is probably what you were thinking.
Yeah.
So there's no angle to.
And it wouldn't be acute like if it were in quadrants 1, you know.
Yeah, so technically saying a reference angle of 0 doesn't really make sense. So yeah, quadrantals do not have reference angles. They cannot.
So that's just something that won't happen.
Yeah, so, and there's actually a quadrantal one that comes up in the next group of problems. We'll probably end up getting to that the next week. Let's see. I'm just looking ahead right fast. Okay. All right, cool. Let's look at problem 4 now. So problem 4, they give us 345 degrees. And so do we have to reduce this using any sort of coterminal association? Nah. It's positive and it's less than 360. Looks good enough to me. So we don't have to swap it out with another more convenient angle. So if anything, we're going to stick with 345. And we need to figure out which quadrant that is, which that normally is just multiples of 90. How many multiples can we use until we run out. So that's 90 degrees. It's 180. This is 270. And then 345. It's not like we have much room left. We know it can't cycle around because we force it to be less than 360. So it's going to go, it's actually going to get really close. So let's illustrate that. So this would be 345 degrees. And so we would triangulate. So naturally, we would want to know the angle of this right here. So we did one in quadrant 2, we did one in quadrant 3, we did one in quadrant 1, and naturally we do one in quadrant 4. So now the question is, what is the last case scenario? What do we do here?
360 minus 345.
Yes. Yes, exactly. Awesome. Yeah. So this one is, so the full revolution is 360 degrees. So that's why we look at 360 degrees minus, well, 345 to give us that blue segment that I drew over here. And that's just 15 degrees. Okay, so does anyone have any questions about this so far? So we can end class a little early. You can tell me 3 songs by Def Leppard.
Pour some sugar on me.
I always do
Picture or something.
Photograph.
Yeah, yeah. And
One more. So you picked the 2 popular ones. So that's why I asked for 3. There's a whole movie with the title as one of their songs with Tom Cruise in it.
I have no idea.
Anyone want to help her out?
Is Google allowed?
What's that?
Is Google allowed?
Is Google allowed? By the time you figure that out, it'd already be 3:15. Rock of Ages.
Rock pages, okay. There you go, there's your third one.
For those of you online, she's wearing a Def Leppard shirt, so I always do that.
I'm so out of context.
Yeah, I always do that. So, all right, cool. Well, that's all I have for today. I'll send out an email and specify about the homework, what's assigned and when it's due and all that stuff and all the little nuances. Besides for that, that's really all I have. If you have any questions, I'll stick around.